Hi guys, in this video I'm going to go through this Leetcode number 239 sliding window maximum. So let's dive into the example. We have a array looks like this, so it has all the numbers, and we also have the window size, in which in this case is 3. It could be any number. It could be 1, 2, 3, 4, just not a negative number. So the task is to look at the maximum number within that window, and then the window will move. When you can see the first window is like this, and the maximum number is right here. The second window, when we move one position away to the right, so it looks like this. So the maximum number is right here for the second window. The third window right here, the maximum will be 5. As you can see, we collect all the maximum number along the way when we move the window along until we hit the right boundary. And there are some trivial case. In this case, the window size is only 1, so we only look at one number and just need to return the list itself. We look at the size of 2 windows, and it's exactly the same size of the input array, and so we return the maximum. So in terms of companies, Amazon loves this question, also Google. So immediately one approach will be have a brute force approach, where we look up all the windows when we slide it, right? There will be a very natural way to solve this problem. Actually, the code is not that bad, right? So that's the code to slide the window and then at the same time look at the maximum and then append it to the answer. And this solution definitely will work, but it will Leetcode will not accept it because it takes too much time. And the time complexity is going to be n times k. So n being the number size and k being the window size. So a slightly improved something looks like this. So that's the explanation of the slightly improved way. So because as you notice that when we move the window, so that's the first window, and when we move to here, so there is a that number is gonna leave, and this number is the newcomer that is coming into the window, right? So the first window looks like this, the second window looks like that, and the third window looks like that, right? So when we move the window, there's always the one guy is leaving the window, and then there's another guy is coming to the window. So and then we can have a comparison, right? So basically, we have the two relationships. One is the guy is leaving, and also the current maximum at the window, current window maximum before the newcomer, and also there we have the size of the newcomer. So if the guy who's leaving is less than the guy at the current max, and also the current max is greater than the newcomer, in that case, the next maximum after the newcomer come in will be the current max, because the old leaf does not impact the whole thing, because the maximum number even in the new window is within this is already captured in the current max. And in the case where the old leaf is the maximum number, and we have to reduce the max function for the new window that we're looking at. And for the case where if the newcomer is the biggest number among all the numbers, and the new maximum will be just the newcomer. And also in the last case where the current max is smaller than the old leaf, but the newcomer is greater than the current max, but maybe smaller than the old leaf, but it doesn't matter because the old leaf is going to be gone. So the new max will be the the newcomer. So for this algorithm, as you can see, so it really depends on the size of the newcomer. If the newcomer is greater than the current max, which does not on the existing window, which does not include the newcomer, so the current max is automatically equals to the newcomer. Otherwise, we do some comparison. as you can see, compared to the old method, this method is gonna improve because we have to only have to reduce the max function in one of these 4 scenarios. However, if the given this is like is monotonically decreasing, so we have to keep doing this max function. So in the worst case scenario, so this is still k times n, b of k times n, but on the average case, this is going to improve compared to the old method that we talked about. And the final method that I'm going to present it to you, and also this one with the optimum method, and this is going to be b of n across various different scenarios, and we're going to use a DAC. Because the reason why we use a DAC is when we append number from the left or from the right, also remove a number from left or from right, the DAC will allow us to use a constant time, a b of 1. So that's why DAC is maybe superior than a list. So let's take a look at the scenario here. So let's say we are given the list looks like this, 111, oops, 111 all the way to 4 and 5, and then the window size is 6. Okay, and then we have a DAC, and then we append a number. For example, the first guy over here, second guy over here, third guy over here, all the way to the fourth guy. Not the fourth guy, it's the sixth guy. And then the sixth guy comes in, and when this comes in, it compares all the guys prior to that. And if that guy is greater than all the guys is already in the DAC, and then we move all the guys who is smaller than the current guy, so that because this guy is all smaller than the new guy comes in, so we don't have to look at them ever again. So that's why it can improve, and this is where we can improve the efficiency. Also, for a DAC, when we remove the guy from the DAC, it only takes a bit of 1. That's why the DAC is coming to play in here. And after we finish the first window, and look at the one and only element. In this case, one and only element. In a general case, we look at the first element in the DAC because the DAC is always decreasing. So the first guy is always the biggest. And then we append that number to the output, and then we slice the window. After we slide the window, and we look at the 5, and the 5 actually is greater than 4. And remember, every number is in the DAC already. If that number is smaller than the current number, and then we will remove it. In this case, yes, it is smaller because it's 4 is less than 5, and we have to remove 4, and now the DAC has only 5, and then we will append the number to the output. So again, so this DAC is always decreasing. All the number already in the DAC has to be at least greater than the new guys comes in, otherwise it's being kicked out. Whenever it's kicked out, and only takes a big O 1 time. That's why the DAC is efficient. So let's look at the code together. And first we have an answer, and that's something that we will return at the end. And we need a DAC, as we talked about. And we need 2 pointers. One is the left pointer, another the right pointer. We initialize the pointer to be 00, 00. And while the right pointer is less than because with the index we're talking about, so it's less than the length of -1. And when, so this is where we kicked out all the number that is smaller, and the new guy comes in. And the DAC actually is only collecting the index, which is equivalent to the one that we saw before, right? This is not indexing, but we can access the original number by using this in Python. We just access this one, look at the right index and look at the number list, and then we can access the original number. So whenever there's something in the DAC, I call Q in this case, if that existing number is smaller than the new guy, we kick them all out, and this is only takes big O 1 time. And after that, after we clean up all the smaller guys in the DAC, and then we append the new guy to it, the new index. And then if the leftmost one, that index, is smaller than the left pointer, that means it's for outside the window. Because the left pointer and right pointer really help us to slice the window, and that the distance between the two will be a k. And if the first index, which is the oldest index, and is smaller than the current pointer, and we have to kick off the oldest index from the deck. And then we check, right? If the current window we're looking at is exactly the same size as the required size, which is k in here, we append a number, which because this is always decreasing, as you can see, because we kick out all the smaller guys all the time. It's always decreasing, so the biggest guy is always at the first one. And then we access that by using this one number, and then look at that index. After we have reached out the window size, we increase the left index, and the right index is always increased by 1. And again, the left index is only increased by 1 where when we have a desired window size, and that's exactly what we need. And this only takes a constant lookup time, not constant, constant time complexity before O of n. And for space complexity, we need a DAC. And in the worst case, if the given number is all decreasing, and we cannot kick out any of them, so the DAC will have a size of a big over n. So that will be in the worst case scenario. That's why B of n for both the time complexity and space complexity. So this is so much for the solution. I hope you like it. If you do, please like this video and consider subscribe to the channel. That will be a huge encouragement to me to make future videos like this. I hope you enjoyed it. Thank you so much for watching. I will see you in the next video.